For those of you who just wandered in here randomly and weren't here yesterday, I'm Ben Goertzel from Novamente and one of the organizers of this conference series. When I saw that there was a workshop organized on self-programming, at first I thought to prepare a presentation on how my OpenCog AGI system eventually will do advanced self-programming and rewrite its own source code and so forth, which is not something that we're doing in the system right now, as those of you who were here yesterday saw. We're involved with making the system do considerably simpler kinds of learning, just learning to cope with a simple virtual environment and learn and reason about what it's doing in the virtual world, or making a robot solve simple problems in a robot lab on its own, rather than more advanced topics like modifying its own source code. We're not nearly there yet. But as I began to prepare that paper, I started thinking more about what does self-programming really mean? I mean, how do you distinguish self-programming from learning? Because after all, any time that an AI system learns new information, in a sense, it's doing some kind of self-programming. Because what is the difference between the knowledge that you've acquired about the world that guides your activity and your programming? Is that really a crisp distinction, or is it a fuzzy distinction between your knowledge and your programming? So I wound up spending some time trying to clarify that to myself. Just what's the difference between learning and self-programming, and ended up just submitting a short paper on that theme, trying to clarify what does self-programming actually mean. And I may not have the same understanding about that as everybody else, but what I'm going to discuss for the next few minutes is just one view of what is self-programming, which views self-programming as a kind of learning, basically just learning about the features of a system that are most critical for its intelligence. So the view I'm going to present is self-programming innately doesn't exist as distinct from learning. You can learn about various things. Some things you learn about maybe kind of inessential to your intelligence, like a phone number, how to play tic-tac-toe or something. Some things you learn about, like, say, how to think about mathematics, or how to feel about your relation to other people. These things you may learn about are more critical to your intelligence and your approach to the world. And I view self-programming as learning about intelligence-critical system features. Then in the paper associated with this talk, I went through some effort to kind of mathematically formalize what that means. What is an intelligence-critical system feature? So after briefly presenting that, then I'll address the question of, is there something fundamentally different about learning about intelligence-critical system features versus learning about anything else? And that really depends on your AGI architecture. I think in OpenCog, there isn't really a profound difference there. At least in theory, in the architecture, learning is just learning. And we believe that as the system evolves and follows its developmental trajectory, it will be able to learn about itself and its intelligence-critical features using the same methods that it uses to learn about simpler things. No, of course, we'll see how well that works when we actually get there. There could be other AGI architectures in which learning about intelligence-critical system features is done by significantly different methods than learning about simpler kinds of content, and maybe we'll hear about some of that in the other talks. So just to start off introducing you to my train of thought, I considered two different cases. So you could consider the case of two different AI systems that do the same thing but with a different underlying software architecture. System A in this thought experiment, System A it's kind of an agent operating system. You have an infrastructure layer that just runs AI agents, and they can interact and adapt with each other. Now, system B is a more specifically hardwired AI system, which contains, say, 10 cognitive processes, say one doing reasoning, one doing learning, one doing concept creation, one doing language. But then suppose in your agent operating system, system A, you implement 10 agents that are identical to B's hardwired cognitive processes. Then what you have here is, in case B, these 10 agents are part of the infrastructure. In system A, those same 10 agents are cognitive content. They're agents that are programmed as content within the system. So if the same 10 cognitive agents are infrastructure for B, but they're cognitive content for A, if those are adapted via learning, is that learning or self-programming, right? Then on the most glib level, you'd say, well, in case A, this is just learning because the system is just modifying cognitive content that it's running. In case B, you'd say that modifying those agents is self-programming because it's modifying its infrastructure. But really, it's quite an arbitrary distinction, right? It's the same thing. You're just using two different architectures. So if you really think about it, the difference between learning and self-programming, in this case, it would just come down to a trivial distinction, which isn't really what you want. And when I think about that in terms of our OpenCog system, it becomes quite concrete because you could implement a cognitive process, which we call a mind agent, acting on our atom space store of knowledge in two ways. I mean, you could program in C++. You can hard code something like a logical reasoning system or a procedure learning system inside the system's C++ code. Or you could implement the same thing in the language called Combo that a previous version of Moshe wrote. And I mean, that it could be the same process. In the case where it's a combo program, that agent is implemented as cognitive content. So the system can reason and learn about it using its current methods. In the case where it's written in C++, it's part of the system's infrastructure. Right now, the system has no way to modify that, but in future, we could enable the system to learn and reason about its C++ code, and then it could. So that's in this case the difference between, say, learning to modify the combo schema or self-programming to modify the underlying C++ code. Again, that seems a kind of trivial implementation level distinction. And you would like the difference between plain old learning and self-programming to be more than just a distinction about the particulars of the software implementation. So the two cases where OpenCog modifies its PLN inference process implemented in C++, which it now can't do. We have an instrument to modify its C++ code. Or case B, where it modifies its inference process implemented as a schema in Combo. Really, like logically and in terms of AI, those are the same thing. We don't want to call one of them learning, the other one self-programming. So how do you work around that? Well, I decided to take a different approach. Think about self-programming as a fuzzy quantity. So if you can measure the intelligence of your system in some way, and if you can somehow divide the state of your system into fairly discrete features, then you can think about the degree to which the feature X is self-programmed as sort of how much does the system learn about that feature X multiplied by how critical is the feature X to the system's intelligence. And in this way, you can just view self-programming as learning about intelligence-critical features. So as a human being, like if I learn about how to throw this thing up in the air and catch it without dropping it, that's not that critical to my underlying intelligence. Whereas if I learn about, say, how to better apply Bayes' rule to aspects of my personal life, right? Then that would be more critical to my intelligence. And so that would qualify as self-programming to a greater extent. So if you accept this, then there's the question of how do you define those two quantities. And I talk about that a bit in the paper. I mean, intelligence criticality, you can basically think about the intelligence criticality of a system feature X is how useful is that feature for predicting the intelligence of the system. And then you can formulate that mathematically. And presumably, how well I can throw this up and down is not going to be that useful as a feature for predicting my intelligence in the environments I usually operate in, although in some environments it could be. If the only way to get food was to throw something up and down and then hit the food, maybe that is critical to my intelligence. But in everyday human environments, it isn't. On the other hand, being able to use Bayesian inference to reason about social situations may be a better predictor of my intelligence and of the intelligence of similar systems. Then you can formally define the amount of learning about something. Similarly, just how much does adapting your ability to do that thing correlate with your intelligence? And how much does learning about that correlate with improvements in your intelligence? And again, for some things you could learn about, that correlation exists. For other things you could learn about, how much you've learned about that thing probably doesn't correlate with intelligence improvements very much. So I won't try to go over the math here, which is fairly simple, but I went through some effort to formally define those things. So in practice, if you want to measure the degree of self-programming in a system, you could choose a randomly selected act of learning the system does, choose it with probability proportional to how much was learned, and say, well, okay, how intelligence critical was that thing? So then if most of the learning is about things that are core to the system's intelligence, that would come out high. If most of the system's learning is about things that are not critical to the system's intelligence, the system isn't doing much self-programming. So this is a sort of viewing self-programming as a case of learning, which is just learning about things that tend to have sensitive impact on the system's intelligence. And then the question that leads up to is, do you need special learning mechanisms to learn about intelligence-critical things? Or can you really just do it using generic learning? And in an open cog context, I come back to the Piagetan stages, which I'm so fond of. And you look at the hierarchy of more and more abstract types of learning, from infantile learning, which is just making sense of simple goals in your sensory motor reality, through concrete learning, which involves a sense of self and reasoning about the specific things in your environment, formal and abstract learning. Then when you get to the reflexive level, which involves a deeper learning about yourself and your relation to your environment, then you're getting to the level where self-programming becomes more profound, and the system, once it reaches this level, which OpenCog and any other existing AGI system is certainly very far from. But when you do get to that level, you have a system where it's able to do a lot of learning about the more intelligence-critical aspects of its function. And in terms of an uncertain inference system, you're talking about having a logical inference system that can learn new inference rules, learn new quantitative truth value evaluation formulas, learn new inference control strategies that are pertinent to different topics, say as inference control strategy for inferring about social situations, an inference control strategy for doing inference about mathematical theorems as separate from, say, scientific content. Once you add a system that can learn new inference rules and inference control strategies from experience and from abstracting from experience, then you'd have a system that's doing reasoning about things that are really critical to its intelligence and would have a high degree of self-programming, according to the fuzzy conception of self-programming that I presented, which is basically given by that simple formula. So this is one fairly rigorous way to think about self-programming, which seems to make sense in the abstract and to tie in with particular things that one could do with AGI systems, like reasoning in OpenCog. I don't think it's the only way to think about self-programming, but it seemed to clarify the concept to me. And I'm curious to see how the other speakers have construed the concept, which we'll see in the subsequent talks. All right. Well, that was 19 minutes, including fiddling with the laptop. So that's not bad. Huh?
So, here and
Good morning. My name is Brandon Rohrer, and I'm from Sandia National Laboratories in Albuquerque, New Mexico. And I'm going to be talking about self-programming in the context of an implemented architecture that does both feature creation and general reinforcement learning. Let's see if I can figure that out. There we go. So most robots today have one thing in common, which is that they work well in a very structured environment, that is with a known model, or in environments and tasks that are easy to create models of on the fly. My goal is to enable robots to work in environments that are very difficult to model and complex, pursuing arbitrary goals, specifically, more loosely speaking, to do everything it is that I can do, including cleaning up or fighting my battles or building a robot or giving a talk, interacting with other humans. And the term that I put on this is natural world interaction. This is a specific subset of the goals within the broader AGI community. You notice I didn't say anything about biological plausibility. My bias is that the most likely way to do this is by mimicking how the brain does it and how people do it. But if I can figure out another way to do it, I'm perfectly satisfied with that. And the current state of my work in this area is captured in a brain emulating cognition and control architecture, BECCA. And you can see it in block diagram form here. There is an unsupervised feature creator in tandem with the reinforcement learner. And you can see the whole thing is set up to be a reinforcement learning paradigm. Observations are taken in, actions go out, and there's also a reward signal. BECCA is set up to make very few assumptions about the tasks that it performs or the hardware that it's implemented on. One of the few constraints on this interface is that all the inputs and outputs are vectors of values, real values between 0 and 1. Each one represents the presence or absence of an attribute or of an action. So you can think of them as binary, but they can be scalar valued. I just want to point you right now to the website at the bottom of the screen, sandia.gov/roar. All of this information, papers, code, videos, it's all there. Feel free to pull it up anytime. So what I'll do is I'll walk through the pieces of BECCA and then give some examples about tasks that I've applied it to so far. The unsupervised feature creator and reinforcement learner have both been created in my lab. The reason is I wasn't able to find anything that does what I needed them to do. I expect that probably someone in this room will create better solutions for both of these at some point, at which point I'll happily replace these. And I'll describe what it is I need them to do here in just a second. The feature creator takes in observations and separates the input vector into groups, so into subspaces. And it does that based on inputs' correlation with each other. So inputs that tend to be correlated are broken down into subgroups of inputs. And then each of those groups, within each of those groups, commonly observed features or commonly observed patterns are defined as features. Then at each time step, as the inputs are processed, the inputs vote on which feature is active at that particular time. There's a winner-take-all process, and within a given group, one feature comes out as the winner. Those are all combined and passed on to the reinforcement learner. These feature activities are also real values between 0 and 1. They look exactly like inputs. So they're fed back and concatenated with the input vector, and they become inputs to this grouping and feature creation process again. This allows for the creation of hierarchical features, of increasingly complex features over time. It's entirely unsupervised, driven only by frequency of observation. So the characteristics of this that are desirable are that it's driven by experience, it's all incremental and online, it's suitable for use in a behaving robot, which is a constraint on all of this work. It continues lifelong learning. There's no separate training phase, and it can handle high-dimensional input spaces well because it breaks them down into subspaces before it begins processing them. So it doesn't get bitten very hard by the curse of dimensionality. It's biologically motivated, which I won't bother to argue right now, but it's fun to talk about over beer. It doesn't assume very much about the task or hardware, and I want to emphasize that it works with multiple and mixed sensor modalities. BECCA doesn't know anything about where what type of sensors produce these inputs, whether they're pixels and it represents whiteness, or whether it's FFT processed audio, or a bump sensor, or a radiation detector, or the presence of a certain concept as determined by some pre-processing step. And the reinforcement learner also has some unique features, some unique attributes. So the feature activities from the feature creator are passed in at each time step. The first thing that happens is those are associated with the reward at that time step. Features that are consistently present when a reward is received are noted. Also, there's an attention step where one feature is selected to attend based on its salience. And that attended feature at each time step is combined with recently attended features, with decayed versions of them. And so you get a short recent history of what's been attended. The current attended feature and recent working memory are combined in a model of the environment. What that allows you to do is note which, if you observed A, B, and C, and then D followed, that transition is an example of one entry in the model. You can think of it like a tabular form of a first-order Markov transition model, where you can extract the transition probabilities based on the statistics of your entries. Using that model, you can look at your current working memory and make predictions about what's likely to happen next, conditional on taking various actions. And then based on that, the action selection block looks at likely outcomes, the actions associated with them, and the rewards associated with them, and chooses either a greedy action or an exploratory action as a result, and then sends that out to the world. So the features, the attributes of this reinforcement learner that are desirable are that it is also incremental and online. It learns which features are rewarded and which are not. Also, it continues to learn over its lifetime. There's no separate training phase. Its behavior is driven entirely by the task at hand. But it assumes nothing about that task to start with. So the status of BECCA development is, right now, all of the code is written in MATLAB. It's all downloadable. I think the most recent version is a couple weeks old. There's new versions go up usually every couple months. It is research code. I'll just leave that caveat. But I do try to make sure that it works. So you can download it, pull it up in MATLAB, and run some of the examples that I'm about to show you. It's separated into agent code that determines the behavior of the feature extractor and the reinforcement learner, and task code. There are separate folders, each containing a different task that you can select between. The ultimate plan is that individual users can download this and then create their own tasks modeled on those tasks using the same interface. We're in the process of porting to Python. This is motivated by a desire to interface with the robot operating system, ROS. It's becoming the closest thing that the robotics research community has to a standard. And because BECCA is intended to be a very broadly applicable, embodied approach, we want to be able to get it on as many robots as simply as possible. And if you've ever worked with hardware, you know that 98% of your pain is just getting the software to talk to this stuff. So something like ROS is really appealing. So in the remaining time, I'm going to go quickly over some of the simple online tasks, or sorry, simulated tasks that BECCA has behaved on, and also mention that our robotics work will be presented tomorrow night at the demo session. There are two students sitting in the front row here, Sean Hendricks and Pei Broger. They've been working in my lab this summer and have been working hard on integrating it with some robots. We brought those robots and we'll be showing them tomorrow night, doing some simple behaviors, but with this cognitive architecture under the hood. So this is an example, a 1 degree of freedom task. There is a white image with a black bar in the middle. There is a frame, a field of view that BECCA has, this square, and it can move it up or down. Depending on the position of that field of view, there's an associated reward. And you can see here that it gets rewarded for centering this window on this black bar. Again, it doesn't know anything about this, the structure of the task. It just gets vectors of inputs and actions and rewards at each time step. And so what you can see here is over the course of time, there's quite a bit of exploration that goes on as the groups are being formed, the features are being created, the reward map is being populated, the model is being created, and then in this case, after about 5,000 time steps, you can see that learning then begins to pay off, and the position tends to cluster much more tightly in this region here where the maximum reward is received. And you can see the average reward jumping at that time. One of the benefits of this approach, as opposed to a lot of model-free reinforcement learning approaches, is that the model is the same even if I were to suddenly change and reward this for moving to one of the extremes. It would keep all of its modeling information, and it would only have to relearn the reward map. That's different than Q-learning, for instance. Here's an example of, this shows in this task the features that are created. And you can see that they look like a black bar at various positions within the field of view. And there's 12 of them. And if you look in the, this is a representation of the reward map. This shows the reward that's associated typically with each of these features. And you can see these where the bar is essentially in the middle are rewarded most highly. This plot here looks a whole lot like this plot here, showing that it learned the reward map pretty accurately and that the features that it's using are useful in accomplishing this task. Here are some examples of some transitions from the model. So if it has this input and moves its frame downward, the black bar appears to move upward. The model is rendered so that we can interpret it in terms of the task. Internally, BECCA doesn't know what it is. It doesn't know this is an image. It doesn't know what it means. But when rendered for us, this is what it is storing based on its experience. Here's a 2 degree of freedom version of the same task. Now it can move vertically and horizontally. And you can see here that after an initial period where it learns the groupings, creates the features, populates the reward map, populates the model, it begins to bring that position in close to the center and stay there where it's maximally rewarded. Here the groups and features are a little bit more complex. Down here on the bottom you can see the groups that it created. If I remember right, there's a little more than 50 of these, and these are, you can see the pixels that tend to be correlated with each other also tend to be located next to each other. Within one of these groups, you can see the various features that were extracted. So these are commonly occurring patterns within this first group of pixels here. It's interesting to note these are groups of pixels and these features. If you look over here carefully at this feature at this group and this group, for instance, these are actually combinations of groups that tend to be correlated. So it's an example of hierarchical feature creation. Similar to how in the human visual system, in V1 we may create short line segments, then moving to V2 and to V4 and to the mediotemporal area, those visual features become more complex and richer. This is designed to do the same thing. And here are an example of some excerpts from the model created in this task as well. Here's a very simple 1 degree of freedom task. Let's see if I can make it play. So the dial can step right or step left. I promise. Nope. Oh, I even tested it. It's the demo demon. Gets you every time. So I'm going to skip that because it's not even the best one. Let's see if we can get any of, there we go. So here's an example of a 2 degree of freedom task. Each of these robots can move the elbow and move the shoulder, and the goal is to get the hand on that little target. So you can see initially, this is like a newborn, has no idea what motions produce what changes in its sensory input. It wanders until it stumbles onto the target and then restarts and does it over again. In this case, it's been learning for a little while, and it moves haltingly, but more or less directly to the target. In this case, after additional learning, it moves nearly optimally to the target. Here's an example with a 7 degree of freedom robot based on a robot we had in the laboratory, Power Cube, and we started working on just gripping a little block. So it was just exploring that 1 degree of freedom and what changes it observed in its sensory information when it gripped that block. And we expanded that to a planar 2 degree of freedom, actually 3 degree of freedom gripping task, and it was able to learn to move to and grip the target pretty readily. And then it was expanded to a full 7 degree of freedom task. Initially, codec unavailable. That's cold. Okay, so initially it wandered in an exploratory way. It was not able to complete the task at all. And then after starting it close to the goal, so it could explore and stumble onto the block, when it became successful at that, it was moved back and moved back until finally, also unavailable, you could start it far from the goal and approach the goal start at a random position far from the goal, and it would be able to achieve the goal. And occasionally it would miss, but it had a good enough model, then it would correct and get it. So as I mentioned, these are all simulation examples. The real goal we're really excited about is hardware, and you'll be able to see the initial implementations of that tomorrow evening. It looks like there's just a couple of minutes left. I'd love to take a question or two. Yes? Yeah, right now it's a big matrix. There's an incremental estimate of correlation that gets updated every time step. It's still by far not the slowest part of the code, but it could be an issue, but it's the type of thing that would be well addressed by the high performance computational tools, GPUs, and things like that. Big matrix operations. So, yes? Can you say that again? How is it compared to? So this feature extraction method, because it's constrained to be online and incremental, it's very dumb. It looks in the subspace of that group, and it looks at essentially the unit vector that represents that feature. And if a new feature comes in that's sufficiently far away, it adopts that as a new feature. So it's a version of imprinting is commonly used in vision processing. But its goal is not to represent the inputs in some optimal way, but to spread those features in some uniform way across the input space that's used. There's lots of regions of that group space that actually it never gets to, so it doesn't have to create features to cover it.
So is it growing neural gas type of algorithm?
I'm not familiar with the neural gas algorithm, so I can't comment on that. Sorry. Yes, I would be interested in learning about it.
I think if we're going to have a coffee break at all, we're going to have to probably pretty much eliminate the questions right after the talks here. So we're going to bring this one over to Pei Wang.
Great.
The next
Thank
talk.
Okay, as you can see, my topic is about how to do this self-programming by a reasoning system. So first, I will briefly clarify what I mean by self-programming. What I believe is the following is kind of like a straightforward, wow, something weird happened, understanding. The first line is supposed to be a definition about what I call a basic action. So anyway, the idea is for any computer system, usually you can analyze its activity in terms of a small set of smallest unit of what the system can do. We can call that a basic action, and then using those things, we can form something we call a program. Okay, a program is just those actions are organized together in a certain order or something, and then the next one is about what is programming. Programming is the process of putting the actions into programs. Then, what is self-programming? Well, self-programming is to do this process not by a human programmer, but by a computer itself, right? To me, that's kind of like a common sense understanding about what self-programming means. Even though it sounds very simple, it's still something we need to clarify. One important issue to me is we all know that a computer system can typically be analyzed or described at different levels of description as different levels of virtual machine. Right? So that means we can analyze the actions and program also at different level. So everyone is familiar with those levels. So at different level, what we call action and what we call program are actually more or less different from each other. And sometimes we use different terminology for them, even though they kind of share the common property, as I mentioned before. It's kind of like action is the basic unit. Okay, a program is the bigger unit which we use to handle a practical problem. So that basically means self-programming can actually happen at any of those levels. Okay? Also, that means when we say self-programming, it doesn't necessarily mean to modify its own source code, even though that's a possibility. Okay. So, for example, source code typically happens when we say it. Usually, we mean the code at high-level language level. Okay. If your self-programming happen above that, it's say knowledge representation level, then it doesn't really change the source code. So actually, Ben already addressed that issue. Also, according to this understanding, many existing AI or AGI technology can be seen as different approach toward self-programming. You can see that this list, each of them actually are based on very different assumptions and use different methods. But in a sense, they can also see as different attempt, okay, to start with a small set of fixed basic actions and then find a way to organize them together. So in this sense, we can call them a different approach toward self-programming, and also that address the issue also Ben mentioned. What's the difference between self-programming and learning? Okay, according to my understanding, well, these two, of course, have some overlap, of course, related to each other. Well, just like everything in AGI are related to each other. But still, these two terminology to me have different focus. Okay, like in my list, the last three are typically considered as learning. The first three are typically not. Okay, of course they're related. So that's about my understanding about the problem. Then the solution I proposed is how to do that. Use reasoning. Okay, this is clearly a big topic. I don't have the time to go into details. So the paper is online, and also there are other related papers. So basically, the idea is also something Ben Goertzel mentioned yesterday. I have been working on a project called NARS. What makes it different from many other AGI systems is I try to use reasoning to do almost everything. Okay, which of course will include how to handle operations. So the basic idea is first to treat an operation as something that can be handled by logic. So to me, or in NARS, operation is a statement, but is executable. Okay, so it's very similar. Well, actually, the idea comes from logic programming, like Prolog. So you can have a procedural interpretation of a statement. Okay, so you can actually make something happen or make a statement true. Okay, like you can walk from one place to another. Well, I mean, for a robot or some simulated system. And then you can define different types of relationship. Okay. Here, the most important one, or two, one of the two is called inheritance relation, which represent a generalization between operations. For example, we can say a walk is a special form of move. Okay, move is a more general concept than walk, even though both of them describe operations. Then another one in NARS is called implication, which is kind of like if, then, or implies. So that one can be used to describe the condition or an effect of operation. Like, for example, if you move from X to Y, then after that it will be at Y. But the condition for that to happen is you need to be at X at the beginning, okay, roughly speaking. Then this should look familiar to many of you because many other technologies use similar things. But what makes NARS a little bit different from many of them is it allows all kinds of uncertainty. So all of the relationship or all the statements in the system are true to a degree. Okay? And furthermore, this uncertainty is measured by a kind of two-dimensional truth value. I use two real numbers between 0 and 1 to indicate the statement uncertainty. The first one, and both of them measures kind of like evidential support. It's kind of like according to the system's knowledge to what degree this statement is true. Okay? The first number is called frequency. It measures how much positive evidence you have among all evidence. First, of course, I assume the amount of evidence can be defined and measured. So it's kind of like probability. But it's not the limit of that ratio, okay? It's the current proportion according to what you already know at the moment. And the second value is what I call confidence, but that's very different from the confidence interval in statistics, even though it has some similar intuition behind them. So the second measurement is use the total amount of your current evidence to compare the total amount of evidence you are going to get in the near future, okay, defined somehow. So it's kind of like how much you already know about this thing. So that's kind of like the basic components in knowledge representation. Then how about reasoning? Well, in a system, there are a whole bunch of inference rules, okay, which include deduction, induction, abduction, revision, blah, 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 a long list. Okay, and each of them has a truth value function attached. So it can calculate to what degree the conclusion is true according to what degree the premise are true, and also depend on the type of inference. Okay. Deduction is kind of straightforward because both the inheritance and the implication I defined before are clearly transitive. Okay. So now it becomes, if it's not in binary logic, it becomes transitive to a degree, especially if I have a two-dimensional truth value and how to calculate that. Okay. Induction, abduction, and analogy are more special in my system. Okay. It's kind of like based on evidence. For example, if the system see event A followed by event B, by induction it will form a hypothesis that usually A will be followed by B. Okay. The next time it will see A, it will use deduction to make expectation say B will happen after that. If that indeed is the case, then that will be positive evidence for the previous hypothesis. Then the revision rule will make the frequency higher and confidence higher. If it's negative evidence, or if that B doesn't happen after that, then the frequency will be decreased, but the confidence will still be increased because you have more evidence after that. Okay? So that's the basic idea. For all the details, see the paper. So you can see that with those inference, you can begin to learn, or the system can begin to learn the condition and effects of each operation. You don't have to teach everything to the system or define everything to the system at the very beginning. Okay. Also, furthermore, learning is also carried out by inference. Okay, so there are some inference rules you see I mentioned in the first item at the end. So they not only derive new conclusions, they also form new compound operations. Okay, so to compose compound operations means, form some structure. For example, the four basic structure in programming language: sequential, parallel, conditional, recursive, which is also responsible for loops, right? So you can see that all of them can actually be derived in this kind of logic, okay? So if you know operation A can have some result, and then followed by B, then you'll see B as a unit will have some condition and consequence. So in the future, you can take that unit as an operation by itself. Okay. So in this way, you can recursively build a bigger and bigger and bigger unit. That to me is self-programming. Okay. So you can see that reasoning can be used for many different functions, as at least here. Clearly, I don't have the time to explain or justify this claim. Okay, but if anyone is interested, I can explain later afterwards how each of the functions I mentioned here can be carried out by NARS. Use reasoning. So compared to the other technologies of self-programming, what's the property of this new approach? Why I think this is an interesting way to do things. Well, the number one, or the most important assumption of NARS is the assumption that the system always works with insufficient knowledge and resource. Okay? It never have enough knowledge for the task, well, usually, except in very trivial or special cases. And also, it never have enough resource to try all possibility. Okay? Concretely, it means the system have finite processing power, okay? Have to work in real time, make real time response, and need to open to all kind of new input, task, and new knowledge, which may be, the task may be beyond the system's current capacity, and the knowledge may conflict with the system's current knowledge. Okay. So that's the basic assumption, which everything else kind of follow from this assumption. Okay. So clearly, as I explained, the system is highly adaptive. It learns from its experience. It's context sensitive in the sense that for a given task, usually it doesn't follow a predetermined algorithm with respect to that task. Instead, I will just use whatever knowledge and resource available at the moment. Try to find the best solution. And here, perception and action are both taken as operations. And also operation can happen, or that perception and action also is organized as a hierarchy. So it can happen at a different level of granularity and scope. Okay. Operations, goals, and events are all handled as a special type of statements, so it can become the object of a reasoning system. Okay, so you can not only reason on propositions, you can also do inference on, for example, goals and actions and events. So it's a special type of statements. Another thing that make NARS different from, say, the two AGI system covered yesterday, okay, is you see here, I don't have different type of memory, okay, even though I agree that there are different type of knowledge, like declarative, episodic, procedural, whatever, okay. But in NARS, the approach is try to use the same format for all of them and use the same memory mechanism to store and process all of them. On the other hand, in semantics, we still agree, there is clearly a difference between different type of knowledge and their some special treatment here or there. But overall, there is only one memory. And also, you see, operations are analyzed as a hierarchy, not always. I don't think it's a good idea to always do planning or self-programming at the basic operation level, even though at the end, of course, everything will be reduced to the basic actions or operations, whatever you call it. Okay, but planning or perception both need to happen at multiple levels of description. And also, the system should be able to learn a causal relationship between operation and the related events by learning and inference. And another thing that makes NARS special is the multiple type of inference. Okay, it's not deduction only or abduction only or induction only. It's many of them unified in the same framework. And also, that's also a big claim I don't have the time to justify. But you can see the basic idea is used to use an extended sense of reasoning. It's not the the normal type of reasoning. I already extended the concept of reasoning in NARS in several different ways, but it's still reasoning in the sense that the process does nothing but produce new knowledge from given knowledge according to domain-independent rules or patterns. Okay, in that sense, it's reasoning, but the logic is very different from, say, first-order predicate calculus or non-monotonic logic or probabilistic logic or fuzzy logic. Okay, similar to all of them here or there, but overall it's still very different because of the basic assumption. And also you can see that for example, in the study of robots, a reactive and a planning-based robot are typically treated as a very different approach. Okay, but from a NARS point of view, it can be seen as a kind of extreme situation in a continuous approach. Okay, so that well, again, if anyone is interested, we can talk about that in detail. I will show you that both reactive and planning can be handled by NARS as a special case. And also, you see that some of the operations will be executed by the system itself, but some other operations actually can be executed by some outside device. Okay, so we can actually build something what I call a hands plus tools model. So what do you have built in as some basic operations, kind of like our hands. Okay, but it can be used with the tools, which are the things like not part of the system, but you can hook it to the system for a given task. Then the system begin to learn the meaning of that operation, which means the precondition and consequence. Okay, but that thing is not really part of the system, except in a certain short period of time. So overall, the goal, well, with respect to this discussion of NARS, is to build something like a general purpose mind. Okay, it can be put into different special purpose body to function. For example, I have a plan to. Everything I mentioned is already implemented in the sense of the inference rules, but I haven't really hooked it up with, for example, a robot, even though I did some very simple simulation. Okay, but that's the plan for the next stage. Okay, so if anyone is interested, we can talk about the detail. So anyway, if this approach actually works, and eventually I hope we can have a general purpose reasoning system which can be plugged into different system and control the special purpose sensory motor mechanism and some other special purpose software and hardware. Okay, that's all. I don't think I have any time for questions, sorry. But we can do that during the break or in the second half of the workshop. Thank you.
Good morning. My name is Wojciech Skaba. The AGINAO is a privately funded enterprise. The title is Heuristic Search in Program Space for the AGINAO Cognitive Architecture. It is the title of my paper submitted to the main conference. I will focus more on the topic of this workshop, meaning self-programming, of which heuristic search is only part of. We are using a robotic embodied approach to the AGI, using NEO robot from Aldebaran Robotics. And since the robot is has a quite limited power, we use an external host to communicate sensory and actuators, and all the processing is done on a host, and the robot is only like a forefront to communicate the sensory and actuators information. So effectively, it is a basic setting for reinforcement learning, and the objective of self-programming is to develop the program to control robot in possibly intelligent way. To give you some insight on what the robot has built in, there is a visual camera 640x480. There are 4 mics in sensory. There are also joint positions and other. And as actuators, there are new joint positions and movements of the joints. There are 2 speakers. There's also a actuator called by us virtual fovea. It is artificial actuator. We use such a spot in the visual area to move around the visual area just to have a better resolution in that area. I have no time to discuss it in detail, but it's not a built-in actuator. And of course, the robot doesn't have any predefined information on the nature of the sensory. There's only distinction between, for instance, visual and auditory sensory, but nothing else is known. And the basic data flow model is like that. We have atomic sensory nodes and atomic actuator nodes, and those nodes that are inside. The atomic nodes are non-removable, and the other, everything is dynamically changing. And all these nodes are examples or cases of a general notion of a concept node. A concept is to mean what concept in cognitive sciences means. And a concept is a program code built into this node, and also I/O structure, meaning how many inputs, outputs it has. There is also type, whether it's atomic or evolved. There are other fields, priority, resources, etc. And of course, there's a list of actions and rewards, values during that come are updated during learning. And so, in general, this may be envisioned in first approximation as a generalized artificial neuron with a program as transfer function. So we have like a 2-step self-programming. One step is generating this code for the nodes, and the other is constructing the whole network structure. However, this approach, this explanation is imprecise, as you can see there is a case of a double link, which doesn't make sense in this configuration. I will come to this later to explain. So in our approach, what we mean by self-programming is managing the concept network. What we mean by this is constructing new concepts, especially the embedded code, which is programs, as I said. It is adding and removing concepts from the concept network. It is adding or removing individual links, because we don't need to remove the whole concepts. We can only update the structure of links in this structure. And there's also evaluation of the concept network. And for the reinforcement learning setting, by state we mean active concept. So it's the output value of a concept, which is a vector, and state is independent on the value. So any active concept is a state. I will come to it soon. And action is the next program to be executed on that output value. So action is selected independently of the current state of this output value. So the statistic is probability distribution or selection is independent, and the executed program is embedded in the next concept. The link points to. So when action is selected, then this next program is in the next concept. So should, for instance, any other concept linked to the same concept, the program executed would be the same. The result need not be the same, as, for instance, one may fail and the other may work, but it's the code is in the next concept. And in case of many inputs, of course, the execution is postponed until all inputs are available. And now, what we mean by concept evaluation, it is probably most important part of my presentation. The concept node is like a long-term program stored on a mass storage device, like on a hard disk. And there's also a runtime node, and a runtime node is an executable of a concept. So it's like in a RAM, a program executed in RAM, and a lifetime of such a program is usually very short, like 100 milliseconds. And it's worth noting that concepts are evaluated by launching their runtime code, and there may be as many as thousands of runtimes of the same concept. Like there's a single sensory atomic node for concept node for sensory, and it may have thousands of copies concurrently executed at the same time, because it's a visual image currently processed. And so if you have two runtimes of the same concept, then their inputs and outputs are specific for this runtime, and not so they differ for different concepts. And here is explanation of this double link. So this is justified by having two independent runtimes. So for instance, if we have a concept of a pixel and a concept of a line, and we want to form a line from a pixel, then it is required that these two pixels are different. Then if they are different, they may be used to be executed in that way. I will skip this. And so one way more to envision our system is like 4 layers. There's a virtual machine layer. It is a computer simulated in software. It is a computer like early 80s microprocessors with about 50 or more instructions, not more, that are fixed but customizable, but in general they are fixed. And on top of this are built small programs consisting of a few lines. And so we may think of this like elements and chemistry built on top of these elements. And these programs built of atoms, of elements, are the real building blocks of the whole structure. So they may change. There's a large diversity of possible programs, and they may change in many ways, and not all may be combinations may be used, and they are sorted out if they are useless, and there are rules of execution, like I will come to it soon. First, I have to say that we use a single data format for all communication. It is an array of integers, and this is what a visual pixel would look like. There's a size of this pixel and row, column, and YUV for the color pixel data. So it is like what is data vector of visual pixel looking like. We use currently 16-bit integers in this implementation, and this is what a processor is looking like. So there are inputs, vector inputs and output, and this is like a black box. And internally there is accumulator and index register, 0 flag, minus flag, and the local static memory. The static memory is shared among all concepts. So should one runtime update the static memory, this is available to the other runtime, it's like multi-threaded programs in C with static local memories. And this is what programs look like after, if we disassemble code, it is very much like microprocessor codes. And we use a number of variables to control execution, and many of them may be attributed features of maybe attributed to artificial economics. This is like expiration time, priority, resources. So expiration time is that there's a deadline, and whatever happens, the runtime is discarded. So it's for instance, how to solve the stop problem or the problem of infinite loop. It is solved by expiration time. There's also priority. This is ordering the order of execution. They are placed in priority queue, and from priority queue are taken first those most highest in the priority. And there's also resources. Resources control how much of the processor time may be exhausted. So it's not real time like expiration time, but it is once the runtime is executed, it is until its resources are exhausted. And it's just a quick look at this. A runtime passes through stages of its execution. It's first in pending state, then it comes it goes to queue, waiting for execution. When it's executed, after it finishes, then it may end in either terminated or exited state, which are successful states, or discard. The discard is, for instance, if running out of resources, infinite loop, or executing an illegal instruction like out of memory. So in this case, runtime is discarded. So there's a lifetime, and once it is completed, then these results are used to update concepts. So runtimes update data of concepts, and concepts decide which runtime to execute next. So there's also such a natural environment parallel we use. The concepts are like species, and runtimes are like individuals of species, and links are dependencies like who is feeding whom. But we have also non-parallels in this comparison. Concepts do not evolve. Once created, they stay until maybe discarded or live forever. And a species may exist even if there is no single individual. That's quite obvious. If there is a concept of letter E and there's no E in visual area, then the concept still exists. And the same code, there's also another difference. The same code may be used in different places. So it's not like one genotype is the same species. We may use in different places. We may use the same code, like adding two numbers can have a different semantic meaning in different places of this whole structure. I should also tell a little bit about temporal patterns, because we have special purpose instructions for controlling temporal patterns. This is a wait instruction that suspends execution for a given time in milliseconds. Like if we are controlling actuator, then we have to wait until this instruction is executed. And we have also a delay instruction that measures the difference between between the current runtime and one of the inputs, the creation times of this. So, for instance, this is an example of how this could be used. There's possibly a concept that measures differences of 3 pixels in visual scenes. So, for instance, if we have a tiny object, we can have like just measure its behavior. You don't have idea what it is, but if it's moving like that, you know it's a mosquito. If it's moving like that, it's a fly. Or if it's moving like that, it's an airplane, for instance. So we don't have to see the structure of this visual pixel, because it's a single pixel. But from movement, we have a match, for instance, that to say that it is a mosquito. So a number of such matches may cause another concept to say escape and run, because it's danger. And here's another example of how the processing of vision is performed. First, an image comes from the robot to the host, and is first compared with the currently stored image. And on the basis of difference between individual pixels, a vector is created if it's beyond a threshold in difference. And from this vector, what is created is sensory atomic visual runtime. So runtime with this value of output in as runtime. And it is also assigned a priority that is currently set to be a difference in luminance, just as an a priori priority that may be then overwritten by other mechanism, and then it's placed in priority queue. So that's how starts the processing of vision. We have also, I'll skip it, there's a mechanism for linking two concepts into one. And here I would like to talk about learning a little bit because it's not in my paper. Contrary to common convention, we use exploration to mean adding new action to a list of actions, and exploitation to executing any action, not only greedy, or because we don't use the on policy, off policy, action selection. There is only probability distribution, and what is more important, if we are in a given state, it may cause many, from a given state may launch many actions. The system may launch many actions, so there is over evidence of actions always. So it's not that I can say what is the next state. And there's a concept of intrinsic motivation. There are many authors discussing that, like Schmidhaber, Bartow, or O'Dea. The intrinsic motivation is borrowed from cognitive sciences to mean operation of an agent for its own sake, not to fulfill some drives, but for its own sake. And so many authors just control the intrinsic reward, which is a related term, and by controlling intrinsic rewards, they control intrinsic motivation. But there are also other approaches, because this is our case too. Most rewarding actions would be most common anyway, but we want also to create an independent mechanism to control the, to push robot into exploratory direction, and we use probability of adding new action to be proportional to this equation, where there's a constant, and in the denominator there's a sum of all rewards, cumulative rewards of all actions. So should there be no actions at all or not rewarding, then probability would be high of creating new actions. And if there are many actions with high reward, the probability of creating new actions would be quite limited. And there's a general question of how in AGI how to reward, what's the ultimate fitness function? It's maybe reproductive success or survival or eternal salvation. I don't know, but no matter what we say about them, it's too distant to be, even in chess, it's very, very difficult to learn in reinforcement learning if we have only win, lose or draw as a reward and nothing in between. So the challenging part is immediate reward, and we use the following approach here. We have rewarding concepts and non-rewarding concepts. Rewarding concepts is one that, for instance, does truncating only. So color image into black and white. It may be still justified by the system because there are descendants and the reward comes from descendants, so it may be useful. And but rewarding concept, this is not non-rewarding concept, but rewarding concepts are done in the following way. The input is like a state space, and this state space is, you may think of this as temporal spatial pattern, not only a spatial pattern. And we do a binary partitioning, and this binary partitioning is done in this way. In the program, there's a conditional jump, and there's either exit or ret instruction. The exit means negative example, and return means positive example, and from this we calculate probability and reward. Okay, so that's end, yeah. Oh, okay. Okay, so we calculate from this reward, and based on this reward, also the robot is rewarded so by giving it more resources to continue that action. I have no time to compare with other approaches, but to make a comment on what Ben said, I would say that to name something self-programming, I need two features. First, I want it to be a Turing-like machine on top, or self-modifiable code, which is unlikely. And this Turing machine code must be executed on a machine that is the programs that are created in some way random or not hand-coded. So that's a bit different approach than all other authors. So that's all. I believe there's no time for more questions now.
Well, all right. I'd like to explain my research a little bit first. In a nutshell, when you write a program, what you do is you're writing a record of your thoughts. And address the other question. What is before your thoughts? So what is the mechanism that makes your thoughts be there in the first place? I studied refactoring, and my approach were computational experiments. So I carried out a number of computational experiments on refactoring trying to answer that question. And in the process, I found several new things. One of them is that I noticed that partially ordered sets are a very good knowledge base. They are universal. They are very simple, and they certainly support the experiments I'm talking about. Then I found a new type of inference that I named Emergent inference. And I discovered only recently, just about a week ago, that Helmholtz in 1850 experimentally proposed what he called unconscious inference, because we have no awareness of doing it, but it happens in our brains. So it's the same thing as Helmholtz's unconscious inference. In view of that, I propose that emergent inference is an explanation for emergence and self-organization in complex systems. And I also conjectured that emergent inference is an explanation for intelligence. Here is my experiment. I start with a body of knowledge. On the upper branch, you see that I provide that knowledge to a human analyst, and the human analyst creates some structures for me, which I call the natural structures. For example, it could be a problem statement, it could be an object-oriented designer, and the natural structures would be the object-oriented design. On the lower branch, you see that the knowledge is first converted to a partially ordered set format, passed through emergent inference, and that gives me some structures that I call the predicted structures, because they are predicted by theory. And then I compare the two, and they compare very well. I did several experiments so far. I wish I had done more, but I did a few. Here is the first experiment ever that I performed, which is where I actually observe the emergent inference. On the left, there is a very simple program in C, very simple, which I selected for trying to find out the answer to my question. All the Greeks are given input, and on the left are the variables. And on the right is a canonical matrix, which is the canonical matrix corresponding to that program. And you see that I have listed the variables along the diagonal of the matrix. And the statements of the program, which initialize a variable, each statement initializes a variable, are listed as A's, stands for argument, as arguments on the lower triangle of the matrix. For example, the statement, I wish I could see a little better here, N equals C plus D means that C and D are predecessors of N in the partial order. And there is an A there in the column of C and another A in the column of D in the row of D. Then there are two red lines that you can see on the screen that indicate flow of information. Now, in any equation, any mathematical equation, and in any computer program, if you will, like this one, there is always a flow of information. For example, the statement N equal A plus D, or whatever it is, C plus D, there is a flow from variable C and from variable D to variable N. Information flows there. And that flow is indicated by the two red lines that I'm indicated there. Please keep them in mind for a second. They will correspond to connections in the brain, neural connections between neurons. So I started refactoring that program. I have considerable experience in refactoring. So I refactor very fast. But I didn't do that. I actually started refactoring very, very slow, one very little step at a time. I would choose a couple of statements in the program that were adjacent, and I will reverse the order of those statements if I liked to do so, following what my brain was saying. So my brain was telling me somehow, well, these two statements are interesting, so reverse them. I did that. And at the same time, well, you see that if I reverse two statements in the program, I also reverse two rows and two columns in the matrix. And that in turn causes the A's, the arguments, to shift, they move around. As I refactor, I can see in the matrix the A moving to different positions. And I did that exercise for a long time. And one day, I realized that what I was actually doing was causing the A's to come closer and closer to the diagonal of the matrix, and the flux lines to become shorter and shorter. So I thought, well, if my brain is doing that, why don't I just write a little program which just permutes the matrix in such a way that it makes the flux line shorter? And I did that, and it worked wonderfully. By doing that, I had automated refactoring, because now I had automatic refactoring. If I run the little program on the matrix, and then the refactoring transformations, what were before, just a second ago, where the transformations induced by my brain are now induced by the program. So the program is telling the matrix, and the matrix is telling the program, and the program gets refactored without my interventions at all. I automated something else that I'm going to tell you in a second. I went one step further. I thought, well, if I can have a little program that permutes my matrix, and that means the refactoring of the program, then there should be something like that in my brain too. There should be something like this canonical matrix, and something like that little program in my matrix, in my brain, which refactors that similar to that matrix which is in my brain, whatever that is. And that is what makes my thoughts to appear. And I create a brain model. If I have time, I'll tell you about it. And it worked. But let me tell you first what is the result. There's the result of the program. You see how close the A's are to the diagonal. You see how short the flux lines are. They became real short. And you see something else. You see one more feature. You see that the matrix is partitioned. Now, each one of those blocks in the partition are objects. They have behavior. Each block has a number of statements, right? This was a program in the first place. So it has statements that do something, executable statements. So those are objects. They have data, so that's an object. Behavior and data, those are objects. That's an object. So apparently I have also automated the creation of objects. You see other things if you look here. You see inference. It's before your eyes. There are features here that are not in the program on your left. For example, you see two different classes of objects, each one with 3 objects each. That's not in the program on the left. You also see, as Ben would call it, intelligence critical value. Because you see information, the classes, the refactoring, the organization, the association between entities here that you are seeing here that were not in the original program. And all that was done automatically without my intervention. Keep in mind that this is a path. So this is not easy. It's easy once you have done it. This is a rigorous mathematical solution obtained from first principles, not a phenomenological guess or an engineering compromise. It is universal. You can do that with any system because you can take any system you want, convert it to partially ordered sets, and organize it into classes of objects the way we did by applying emergent inference. It is a side effect of an unrelated process. More on that in coming. A side effect is not intended. I say something more in a second. It requires no specific domain knowledge. You can put any subject this to any learning process on any domain, and it will happen. And best of all, it is ready for use in computers. Here are my claims. I claim that any system has a natural hierarchical structure that can be found by emergent inference. And my 2 conjectures I already mentioned are that emergent inference explains emergence and self-organization in complex dynamical systems, and that emergent inference in the brain gives rise to intelligence. Now to the more practical things. Some people ask me, or worry or are concerned about, well, it's probably very difficult to convert a system to partially ordered sets. Imagine that. Actually, it's very easy. What do you do if you have a system and you want to perform a mathematical analysis of that system? The first thing you do, you need a theory, you develop a model of the system, and you write some equations by that theory. Let's say z equals some function of x and y is one of those equations. Conversion of that equation to partially ordered sets is immediate. the set is XYZ, and X precedes Z and Y precedes Z. Why? Because you can calculate Z without calculating X and Y. That's the whole conversion to partially ordered sets. It's a lot easier than solving the equations, and you know many people are, in fact, solving the equations to understand the systems. In a computer program, it's even easier to convert a computer program because it has statements and all the precedence relations are just there. You just read them. All you need is a parser. Conversion for a computer program, the degree of difficulty is at the level of compiling the program. That's the degree of difficulty it has. I wrote a parser for C, it works. Some C, let's say. And finally, I developed a brain model, which I call the CFS brain model. C stands for connecting, F for fire, S for shrink. C and F you already know. Shrink means that the neurons, once they establish their interconnections, those connections shrink. They start making shorter because they try to save energy in the transmission of information. The shorter the connection, the less energy it wastes in heat or in chemical energy for the transmission of that information. So the reason for that, the motivation for S, is the shortening of the connections between neurons. But the result of that is the following. The connections correspond to the flux lines that I asked you to keep in mind for a second. By shortening the connections, they are shortening the flux lines in the canonical matrix. In my canonical matrix, the one in my brain, and they are becoming clusters of neurons, which correspond to the objects that we have just observed in the matrix. There is confirmation of that. One of the confirmations is that Helmholtz, as I said, he's a physiologist, he studied vision, and he observed the unconscious inference. The other is that recently in 2006, they observed what they call neural cliques, which are the clusters, highly interconnected clusters of neurons in the brain, in the cortex, which are weakly interconnected among themselves. And now they are discovering already hierarchies of those cliques. So that's how the brain is. In case you were wondering, okay, nice, emergent inference is great, but how does the brain do it? Well, this is how. Now to more practical things. This represents a traditional process of programming by a human programmer. The brain is represented on the upper row, and the structures it creates on the lower row. So there is a stream of experience that's called knowledge. It goes to the brain. You talk to the analyst. You don't talk to if you are a user, you talk to the analyst, not to the program. And the analyst thinks of what the subject matter engineers are telling him and creates some structures, which are going to be the program, the final product. Okay? I have it here. I thought that was the time remaining. Okay. And then at some point, the analyst is gone. You disconnect the analyst, he's gone. And only the structures remain. Well, I'm afraid I claim that these structures are basically zombies. They cannot update, they cannot learn, except to the extent that the human programmer has told them to. But that's what the program is. And now you can input, it still works, it does some function. You can still send the stream of experience to the program, which now is called data somehow, it's changed the name, and you have the program. I skip that one. And here's a comparison between traditional AI and AGI. Not a comparison, just a thought about that. You have a program that drives cars, connect the position sensors, and the car controls. It will drive your car. You have another stage control program. You connect the stage, the theater stage controls to the stage control program. It will control the stage. But if you connect the red arrows, it will not work. And there is nothing you can do about it. You cannot tell it to the program, go ahead and integrate yourself. There is no integration and no refactoring. Can I take one more minute?
We're a little behind.
I'm sorry?
We're a bit behind.
I try to do, okay. That's how the brain does it. That's how emergent inference does it. Which one looks more like the brain? You'll be the judge. In conclusions, I conclude that self-programming requires AGI, full-feathered AGI, and that AGI cannot be achieved by writing programs. AGI is a process that requires emergent inference. Thank you.
I assume this is de rigueur AIware for Google. Okay, let's see, let's go ahead. All right, I just want to remind everybody about production system programming. This is a fairly standard programming model in, let's see if I can make that disappear. No, I guess not. Okay, a fairly standard programming model in artificial intelligence programming, most commonly used at Carnegie Mellon, but basically you have this just big pile of if-then rules, and without running them sequentially, you just have some hardware or software that whenever an if rule happens to be true, the then rule fires and changes the state of your memory. And the if rules can take off from both memory and input. And obviously, this being a very parallel kind of process can use appropriate accelerating hardware. The basic idea of the approach here is simply that you can get a big pile of if-then rules simply by watching somebody do something. If you can parse out what a situation is in which somebody does something and then parse out the action, your memories, appropriately parsed, follow from into the style of a production system program. The key addition is that you don't ever have a situation that you remember that matches exactly the situation that you're in, and so you need some way to modify the match. And what I'm doing is I call this analogical quadrature, and it's roughly the same sort of thing that Hofstadter and Mitchell's copycat does. You force a match with a situation, and then you carry that forcing over to the action in a parallel sort of way. And the basic the talk is essentially about what architectural features in software and hardware would be necessary to support this kind of programming of a system's own self by its simply watching and imitating. So the key element, I think, is actually that its representation needs to be an abstraction hierarchy. You have to have the situation represented as a whole bunch of different kinds of concepts at different ontological levels. And then you have also things like the parallel processing that it assists with the production system execution, and the next two, the abilities of the representations to take part in the analogical quadrature type operations. And finally, given the abstraction hierarchy, you need a way for the pressures that are evolved in the matches to move up and down the hierarchy in such a way as to affect other levels as well. Okay, the key item for the abstraction hierarchy is simply that when you are matching a situation or an action, there are three levels in the hierarchy. There are actually ranges. You have many levels, but at the very higher levels, you get an exact match because you're looking at an abstraction of the situation. So if I'm a Sherdlu type robot and I'm trying to imitate someone picking up blocks, at the very highest level, the description of the action is simply pick up blocks, and that matches exactly. At the very lowest level, the hand-eye motor control is not exactly the same at all, and so you can't really match that, and you have to do that by some kind of control or trial and error or planning or what have you. And the middle levels, the ones in between, are the ones that are actually susceptible to the analogical quadrature operation. One of the main reasons that you do want the abstraction hierarchy, however, is because since you're representing the situation and the action that you're looking at lots of different ontological levels of abstraction, you can actually be imitating more than one thing at the same time, and that gives you a lot more coverage in terms of the kind of memories that you have to work from than if you only had one particular kind of action that you were imitating. Okay, this has all been done before by evolution, and the architecture here is evolutionarily inspired, and I don't need to say much more about that. If, for example, you're trying to parse a sentence and picking out individual words, you use your parallel matching hardware, and each one of the words that you're trying to match there is again essentially just a memory of a word, and so that feeds into your need for parallel hardware and your use of memories as items in your rule base. In the copycat program, if you have studied it, there's a whole lot of work about slippages in taking a concept, forcing a match with some other concept that doesn't work, but because you're forcing the match, you say, okay, something in concept A has to look like this thing I didn't think it was in concept B. And when you do that, you can force a change that they called a slippage in one of the fields, say for example of a record that describes something, and then you carry that change across from the situation to the action, giving rise to the analogical quadrature. One of the cool things about that is that you can decide which parts of a concept is salient for a given match by having a theory of causality. If I pick up a block and it doesn't fit on another block, I'm more likely to believe that was because of its size or shape than because of its color, for example. And I can derive a theory of causality by the same kind of memory-driven programming, and use that to give rise to an explanation-based generalization parse of the situation that allows me to pick out the salient kinds of attributes of the things that I'm matching. Okay, the key to this, of course, is parsing the action sequences that you see in order to imitate them in such a way that they make sense. And I claim that parsing action sequences and parsing sentences is a very similar kind of operation. In fact, there's plenty of evidence that the same parts of your brain are involved in parsing sentences and generating them, and parsing sequences of hand operations and actions and generating those. And so they're probably very evolutionarily linked and similar. Okay. The other aspect of representations besides there being plastic is that if you can have them be metric, if you can use n vectors, numeric vectors for your representations, and you've mapped the spaces right, analogical quadrature turns out to just be vector algebra. It's very simple to do. And there's also a lot of reasons that you want to use representations like this if you can, basically because it's just a huge backlog of scientific, statistical, and machine learning software that already operates on things like this, and people understand them very well. And so the more that you can use metric type representations for your systems, the better the analogical quadrature and the imitative programming will work. Here's a case where Google Books doesn't do this right, and this is a breakdown in level communication. If you look at this is from the second Oz book by L. Frank Baum, and it gets the title wrong. The actual title here is The Marvelous Powder of Life, and you see what happens is it's clipped the picture out and also taken out part of the capital T, and then its best guess at what the rest of the capital T is as an I, and that forces it to decide that the H is a K, and the only word it knows that starts with IK that might actually be there is Ike. And so what it's doing, obviously, is missing any kind of semantic feedback from a high level that would make sense out of what it was doing. Anybody that actually looked at the page would never guess Ike marvelous powder. They would just look at it and say, of course, it's the marvelous powder. That's the kind of thing that you get from having the appropriate two-way communication between levels of your abstraction hierarchy, and it keeps you from making mistakes like that. All right, so the bottom line is essentially writing programs is very easy. All you have to do is just watch and